Anyway, let's get started with this example. We start by looking at the denominator and factoring it. Hopefully, you recognize that this is the difference of two perfect squares, and therefore can be factored like this. We have once again a difference of two perfect squares here. Not here. There is no factoring for a sum of two perfect squares. So the first binomial is factored like this. The second binomial remains as it was. So this now gives us our new denominator. Of course, the numerator remains as it was. We now can see that we're going to need 3 partial fractions. We need a denominator of x plus 2, x minus 2, x squared plus 4. The numerators for these first linear terms will consist of single letters. The last term is quadratic, so here is where we need cx plus d. All right. Moving to a common denominator. For these partial fractions, a has only x plus 2 under it, and therefore needs to be multiplied by x minus 2 and x squared plus 4. Move on. Plus b. It has x minus 2 under it, so it needs x plus 2 and x squared plus 4. Plus the binomial cx plus d has this under it only, so it requires both x plus 2 and x minus 2 here. Okay, so our large equation comes from equating the original numerator to this new numerator. And it is a big one. I'm going to try to fit it across the page. And as soon as we have that written, we can try solving for A, B, C, and D. How do we begin? We begin by recognizing that we have two roots, x equals negative 2 and x equals positive 2 will work as our roots. So let's begin by substituting negative 2. In the left side, this will be 5 times 4 plus 8. Or 28. In the right side, if we substitute negative 2, we will have 0, negative 2, 0. The only non-zero term is here at the front. Negative 2 minus 2 is negative 4 in here. Negative 2 all squared is 4 plus 4 is 8. We find, this of course is an equation. 28 is equal to negative 32a, from which a is found by dividing 28 by negative 32. Use your fraction button if you want. 28 over negative 32 is negative 7/8. Sadly, we have a fraction. Substitute the next root, which is 2. On the left side, we'll have 20 minus 8, or 12. Substitution of 2 here eliminates that term. 2 here eliminates this term. The non-zero term is here. 2 plus 2, 4. And here, 2 squared plus 4, 8. We find that 12 is 32b. Reduce that fraction, 12 over 32. 12 over 32, 3/8. We are out of roots. We've only solved for A and B. We still don't know C or D, so it's too early to arbitrarily substitute a value. We have to use coefficient. What is the highest power? You can't tell simply by looking at the left side. The highest power possible on the right side is x cubed. Let's investigate. On the left side, there is no x cubed, so we assume 0x cubed. On the right side, where are the cubes? Oh, there's one, ax cubed. Here's a second one, bx cubed. Is there a third? In fact, there is. This gets you up to x squared. When you multiply it by cx, you are up to x cubed. So we have ax cubed plus bx cubed plus cx cubed, like this. From which we get the equation a plus b plus c is 0. Well, a is negative 7/8 and b is positive 3/8, which means that 0 is equal to a negative half plus c. You can add these with your fraction button if you like, or recognize it's negative 4/8, which is negative a half. And that means c is 1/2. Bring this to the other side. And we have just one remaining unknown, and it is d. We can use a coefficient again if we like, but since we have just the one unknown left, and since I've never substituted x equals 0 yet, I might do that. Substitution of 0 for x on the left will give us 0. On the right, what will we have? We will have a times negative 2 times 4 plus b times 2 times 4 plus. Now, a 0 is going here, so this only will be a d. D times 2 times negative 2, from which we get negative 8a plus 8b minus 4d is equal to 0. But we have values for a and b. So this becomes positive 7 and positive 3. That's 10. So we now have 4d. 4 times d is 10, or d is 10 quarters. In lowest terms, that's 5/2. Okay, so now we've got everything determined. We can go back and substitute those values and proceed with the integration. So I'm going to be putting those values in here. So it will be negative 7/8 over x plus 2. It'll be 3/8 over x minus 2. And 1/2 x plus 5/2 over x squared plus 4. Okay. Time to consider these carefully for integration. No problem here. That's a natural logarithm. This will simply be the coefficient. Same story here. natural logarithm with a coefficient of 3/8. Is this a natural logarithm? Well, it meets one criteria. The exponent down here is 1. What's the derivative of the bottom though? It's 2x. So if this term, 5/2 here, wasn't there, we would just have 1/2 x up top. 1/2 x is a multiple of 2x. So we would have a logarithm in that case. So what does that suggest we do? It suggests we split this. We leave 1/2 x in the numerator of one fraction. We move 5/2 into the numerator of a second fraction. Each of those fractions has the denominator x squared plus 4. And I now have 1, 2, 3, 4 things to properly integrate. So this one now will be a proper logarithm. We have to make a little bit of an adjustment to it since again what we want on top is 2x, not 1/2 x. What will this be? You might have guessed it. This baby right here. Okay, so let's continue to clean up these terms a little bit. If I put that there, do we still see the top line? Yeah, we're good. Okay, so we're gonna change the look of these a little bit. Okay? So for the first two, it's really not an issue. I just slide that coefficient forward, leaving a 1 on top. So this will be ln x plus 2, ln x minus 2 with these coefficients. Okay, something a little bit like that here. The key here is that we want 2x on top to make a perfect logarithm here. But we didn't have 2x, we had 1/2 x. So we need to put 1/4 in front here because 1/4 times 2x is 1/2 x. For our last one here, we want a 1 on top, much like we did for these ones. So we simply put the 5/2 here, leaving the 1 on top here. Okay? All right, now we're going to integrate all of these. Okay, so this one was huge, right? We said 1/4 times 2x is 1/2 x. Why did we want 2x here? Because 2x is the derivative of x squared plus 4, and now this will be a perfect logarithm. Okay, for this guy at the end here, of course, we're going to use this formula. What is our u and what is our a? U is x and a is 2. U squared plus this is a squared. Okay, integration. -7/8 ln of x plus 2 plus 3/8 ln of x minus 2 plus 1/4 ln of x squared plus 4 plus 5/2 times, okay, 1 over a, arctan u over a. 1 over a, arctan u over a plus c. Okay, this is 5/4 now. I'm going to combine these in a moment. I might want to write the last one, this one last, since it's negative, okay? So I'm going to do that for this last step as well. Actually, it's not quite the last step. You can see I've abandoned the ruler and everything. Things might be getting to be a bit much for me. Okay, so this one, and then this one. And now I'm going to write the negative one. Okay, because you know we're going to combine these logarithms momentarily. This is now 5/4 arctangent x over 2 plus c. Okay, and I can combine these right now. These would be the strange exponents on them if I did that. I might actually want to common factor 1/8 from all of these coefficients first, because then that would give me a 3 here, which is quite a bit nicer, and a 2 here. Uh-oh, I don't even have a lawn. Oh, my. I lost the lawn, guys. 2 times the ln of x squared plus 4 minus 7 times the ln of x plus 2. And this would be 10, actually. Arctan of x over 2. Okay, plus c. Check that, right? 1/8 times 3, 3/8. 1/8 times 2 is 2/8 or 1/4. 1/8 times -7 is -7/8. 1/8 times 10 is 10/8 or 5/4. Okay, only these coefficients have been changed by common factoring here. Why did I do that? Well, again, just because now these become the exponents and they're integers. Okay, so that's a cube. That's a square. And this one will be a 7. Okay, let's make this tidier by combining them. The rules, of course, for the logarithms are here, the properties of logarithms. But essentially, these combine into a product of arguments and then a quotient. So what I'm trying to say is this. Multiply those arguments together. Oh, the ruler comes back. Divide by this argument because it was preceded by the subtraction sign. Absolute value here. And then my arctangent term. I think we've done it.